We'll take a look now at Module 8. We're going to look at polynomial functions. Let's get ourselves all set up here. Making good progress through the course, hopefully, keeping your paces going. So what is a polynomial function? Poly for many, nomial for I'm not sure what, but what in math we call a polynomial function is defined as something looks a little overwhelming maybe, um, but it's some power of x, and the powers have to be integers. Well, not just integers; they have to be natural numbers and non-negative integers. But they're counting numbers. They're either 1, 2, 3, 4, 5. So that's something like x to the fourth power. That is a polynomial. They have coefficients. In this case, the coefficient would be 1 if we just had x to the fourth. So we'll look at some examples. But the cool part about all of this is while a polynomial could get long and extended and have many parts depending upon how big it is, uh, when we talk about the graphs, there's really only two parts we need to consider. The leading coefficient tells us a lot, and all we have to consider, we don't have to consider how its value, but whether it's positive or negative. That's what it tells us. Okay, but not alone. It tells us the positive or negative value will tell us something about it, but the key part really is this largest exponent n. N is called the degree of the polynomial. So in this case, this function f of x equals x to the fourth, the degree is 4. And by knowing, and then the coefficient in front is positive 1, knowing that we'll be able to tell pretty much what's going on with this function, what the graph would look like. So that's the whole key behind this. So here's a few examples. These are polynomials. Notice the exponents are positive integers, we'll call them that. This 2 would be x to the 0 if you wanted to have an x value in there. So there really are always exponents involved somehow. This has a exponent of 1, t to the 1 power. Notice it's okay to have a radical, but not in the exponent. We'll see that because that would be a fractional exponent or a non-integer value. So integers, right? Things that are not polynomials. So if we have a rational function, this x down in the denominator, what that really is it's 2x to the minus 1, if you remember that from intermediate algebra. If not, but we can't have negative integers. Well, we can, but we can't if we're going to be talking about polynomials. Okay, so these are not polynomials. A square root is really, it's really a 1/2 power is what we'll find out probably sometime later when we look at radical functions. But or maybe you've already looked at them. But anyway, this is not a polynomial. So in this section, we don't have to worry about it. And again, here's a negative exponent. So we're not going to worry about any of these types of functions. Okay, only these ones with nice integer values. And again, the important part we're looking for is what is the largest exponent. So on this last one here, we're just going to say it has a degree of 4. And then it's got a leading coefficient that is positive, a positive leading coefficient, which just means the number in front, coefficient. There's a spelling up here. Okay, so that's the main thing, and then we'll be able to tell everything. Well, let's see what are the properties that result from knowing these items. Okay, the two main considerations we're looking for are what happens when x gets really big, so what we call in behavior. So this is as x goes to negative infinity, or as x goes to positive infinity, is the graph, what's happening to the graph? What's happening to the y values? Are the y's going to positive or negative infinity, or what's happening? And we see that that's pretty much what happens is We'll talk about those. So two main considerations in behavior and multiplicity. Multiplicity is talking about zeros of the polynomial. These are also referred to as x-intercepts. So when we use the word zero, this is code for y equals 0, right? Because that's what an x-intercept is. It's a place where y equals 0. And what we're going to find is multiplicity that refers to the power, the degree, not necessarily just of the polynomial itself. So the degree of the polynomial is the largest exponent. But what we're going to see is it's the degree of the zero. And we're going to see that different zeros have different degrees on them. And that will tell us their behavior as they cross that x-axis, or whether or not they cross that x-axis, when they bump into the x-axis. And what we're, just to kind of let you know, let's just do a big old x-axis here. There's three things that can basically happen. Multiplicity of 1, it will pass directly through. Multiplicity of 2, or an even multiplicity, it will just touch the graph, it won't actually pass through it. So this is we'll mark that as a 2, or 1, 2. And then 3, or if it's odd so 2 or even. We'll talk about them individually as well. We get that with the odd, so 3 and larger, it'll cross, but it might kind of do this one of these sort of things. So it crosses through directly or indirectly. Let's put it that way. So this is for odd 3 or larger odds. So that's what's going to happen. And again, end behavior is on the graph, whether y goes to negative infinity or whether it goes to positive infinity as x is going towards negative infinity. So that's, there's the left side of the graph, left end behavior. And then there's the right side of the graph, or the right end. What's happening? Does the graph go up to positive infinity? And then we're talking y values. Do the y values go to positive infinity, or do they go down to negative infinity? These are y values. And that's as x is going towards positive infinity. So as x gets really, really big, what's happening to y? Is it getting big in a positive way or big in a negative way? Negative is getting small, but these are the things that can happen. And the thing is, we will be able to determine in behavior and multiplicity for the most part by knowing the degree of the polynomial. Now the multiplicity, we've got to, since it's what's happening sort of close in, we have to look in more detail. But the end behavior will be evident simply by knowing the degree and the leading coefficient. Okay, so there's 4 cases for the end behavior. And again, it will depend upon whether that leading coefficient is even or odd. Leading coefficient, positive or negative. So this is the role that the leading coefficient plays. Even or odd, this is telling us about the degree of the polynomial. And again, that all we focus on is the largest. And so case number 1, so even and odd. So let's go with the evens first. Let's say we have an even degree. So that's 2, 4, 6, 8, so forth. So we get, whenever we have an even degree, it's going to behave like a parabola, like a quadratic, which we just talked about. So it will either, and that's why we do this one first, it's really the easiest. The more degree, the larger degrees, the 4, 6, 8, what happens is we may get some squigglies in between, okay? This one is opening up, again, with the squigglies in between, and it could cross the x-axis or something, but the main thing we're looking at for in behavior is that this is what we would just say it opens up, and this is with a positive leading coefficient, right? And so what we see is as x is going towards negative infinity, y is going towards positive infinity, and as x goes towards positive infinity, y goes towards positive infinity as well. So what I like to say with this even degree and positive, positive gives us a, and whenever at least I'm dealing with positive things, I think of a smile, right? It's opening upwards. So in that case, if we have even degree, but we have a negative, let's change over here, a negative leading coefficient, um, we're going to get something that opens downwards. And again, it could do stuff like that, but we get a U shape overall. So negative, as x goes towards negative infinity, y goes towards negative infinity. As x goes towards positive infinity, y goes towards negative infinity. Oops, not 8. That's how I used to make an infinity. I'd draw an 8 and turn it on its side, but with tablets it's not as easy to do as when you have a piece of paper. Let's see, there we go. Okay. But again, I see the negative, and negative makes me frown. So that's what we get. So then the other two is a little bit harder to remember maybe, but we can work with this. This is for odd degrees. And more than remembering all the details about which way it goes to positive, I just draw the graph and then I can see exactly what's happening for each of these situations, right? Because that goes there, that goes there. I know what's happening. So when I've got a odd degree, and that'll be, I guess we could start with one, but that's the boring one. That's just a straight line, right? We'll look at 3, 5, and so forth. What ends up happening is we get what I call the swirl cactus with one arm up and one arm down. So the first one I want to do is sort of in the positive direction. We get this sort of thing, and again, we could have some multiple stuff, but with odd degrees, remember this is what gives us spinor symmetry. So they're always going in opposite directions. So with the positive leading coefficient, negative, as x goes towards negative infinity, y is going to go towards negative infinity. So that those match up, right? Negative times negative is a positive. Also, as x goes towards positive infinity, y is going to go towards positive infinity. So the swirl's cactus has one arm going down the first, and then the left arm, the right side of the graph is going up. So this is our standard for a positive lead. Negative and negative, so the signs are going to be the same. It's a way to kind of remember that. When we have a negative leading coefficient and an odd degree, so let's switch back here, negative lead, then we get the opposite. So it's a reflection around the x-axis. So we get things are, and again, we could get as many humps in there as there are degrees. And you'll see if it's just a third degree, there's just sort of an S-curve through there. So yeah, negative, as x goes towards negative infinity, over here y is going towards positive infinity. So we would get a positive times a negative gives us a negative, negative lead. Over here, x is going towards positive infinity, but y is going towards negative infinity. Okay, so that gives us the four different cases of in behavior. And this is also in the notes and written up. So, but that's the way to kind of remember it. So that's leading coefficient, what it tells us, depending upon whether we have an even or odd degree. Secondly, we're going to talk about the multiplicity, the three types of zeros, and we've written them out. What we'll do is we'll explore this a little bit using some examples. So what I'm going to do is let's just look at this one. I'm going to kind of show how this goes, x minus 3. So I'm going to do it with a 1 power. I'm going to do it with a second power, so that's 2, a multiplicity of 2, and then we'll do it with the same one, x minus 3, with the multiplicity of 3. And the reason I'm choosing this is now if we let y be equals 0, we can see each of these, all of these, have a 0 at x equals positive 3, right? Because you take your x minus 3, set it equal to 0, add 3 to both sides, and there you have it. So what we're going to do is we're going to look at, using Desmos, we're going to look at the behavior of the graph as it goes through this x equals 3, 0. And we'll see the difference is that the first one with multiplicity of 1, see a positive 3, it's going to go straight through. Think like that. Yeah. Sometimes directions we get a little mixed up on, but something like that. Okay. When it has a multiplicity of 2, what it's going to do, and I'm guessing a little bit, sometimes I'm a little off, since it's going to have a positive, it's going to open upwards. So at 3, it should behave something like that. Okay, so we get a parabola as we're getting an x squared, but it just touches the graph. And then finally, the multiplicity of 3, and again, any odd multiplicity higher would have a similar type active. At 3, it's going to go, and again, thinking of the end behavior, it's a cubic, so it's odd power, we're going to see, and it's got a positive, so it's going to do something like this. So it goes through at 3, but it does a little jig, I guess we could say. So let's use Desmos to explore this, and go ahead and keep those for now. We'll go to Desmos. Calculator. Let's go there. Here we go. So we'll graph this one, and we'll first look at, we'll just do this y equals x minus 3. Remember, that's the first power, and then we see it going straight through. I'm going to leave this on, and we'll do another one. We'll say y equals parentheses x minus 3, and we'll square that one, and we see it's just touching at that. I could have chosen a different value, but I just want you to see that they all have the same 0 at x equals 3, but there's a different behavior here. So the blue with a multiplicity of 2 comes down and just touches the x-axis. And then finally, let's take a look at what happens when we have y equals x minus 3. Close it off, and this time we're going to make it a cubic. So we'll go up with the little a to the b, and we'll make that a cube. And you see that it kind of meanders its way. So instead of going straight through, it comes in. So let's do this. It kind of does a little jig, and it still only goes through in one place, but it kind of gets close to it, and it does this. And just to show you that it'll do the same, I could have, I didn't have to, well, I could just change this. Let's do that. Let's make that 5 instead of a 3. And notice it's a little bit flatter, but same type of behavior. So we would say this has again, and the only reason we know that this is a multiplicity of 5 is because we see the, um, is because we're able to see the degree right here. It's also, notice it's flatter, so visually you would be able to see, hey, that's looking pretty flat. That's maybe not a cubic, maybe it's a fifth power. The higher you go, it gets a little, it's, probably difficult to tell the difference between a 5 and a 7. But anyway, any odd power larger than 1, so 3, 5, and on, is going to do that sort of get close, do a little sort of S-curve type thing, and then go through. All even powers just go through there. Again, you could kind of explore these with an even power, say a 4 instead of 2. It'll do the same thing, but it'll be a little bit flatter. So let's just change that to a 4. And you see, same thing, just comes down, touches the x-axis, but has sort of a flatter base. Okay. So each of these, so this would be a multiplicity of 4. Behavior looks very similar, but that's how we can tell the multiplicities. Okay, so there's 3 types: straight through, bouncing off whenever we're even. This is the even case. And this is an odd power of multiplicity of 1. This is odd of 3 and higher. Okay, so that's really all we need to know about polynomials as we talk about them. So we're going to look at these examples. We're going to take and try maybe to draw a few graphs, and we'll see how this works. So when I look at this polynomial, it's actually been made to make the zeros easy to find. So if I set this equal to 0, since everything is being multiplied, all I got to do is look at these factors. So what this is telling me, x minus 2, even though it's squared, is I'm going to get a 0 at x minus 2. So x minus 2 is going to give me, when that's 0, everything else becomes 0. Okay, so that tells me I get a 0 at add 2 to both sides, x equals 2. So you just kind of focus on, it's going to be the opposite of the signs up here. I'll get another 0 when x plus 1 equals 0. So that's going to tell me when x equals negative 1, the opposite of the sign, right? Because you put negative 1 plus 1 gives you 0. That gives me 0. And then the final 0 is x minus 4. That's going to give me a 0. And so I add 4 to both sides, x equals 4. Now this 2 on the front doesn't do anything. Now be careful, sometimes you'll see 2x. Had it been 2x, then also 0 is a 0, right? Because if I could put 0 in there. But this, when it's just a number, there's no variable there. It's just going to do a stretch, right? Vertical stretch, because it's on the outside. Now, from what we talked about, each of these zeros has a different multiplicity. This has a multiplicity of 2. So yes, I just put it here. This would be 2. This one has a multiplicity of 1, and the last one has a multiplicity of 3. So that's part of what we're going to be identifying we're using this. Now, the overall, if we wanted to look at end behavior as well, what we'd have to do is say, okay, what's the degree of this polynomial? We actually are going to add all 3 of these degrees together. So we'd add 2 plus 1 plus 3. So that's going to be 4, 6. It's got a degree of 6. So for end behavior, it's an even. We can just say we've got a negative here. Somehow we know it's going to do some things in between. We've got one at, I guess we could sketch this graph. Let me give myself a little bit more room here. Let's go here, see if we can sketch this. And then we'll use decimals, as we're seeing here, to actually draw it and see how we go. So it's got a degree of 6, which is even. It's got a negative leading coefficient, so it's going to be a frown. But in between, we've got a multiplicity of 2 at x equals 2. So there's one here. Negative 1, we get a multiplicity of 1. And then at 4 would be about here, we get a triple. So we know it's a frown, so it's got to come from here. So it's gonna come down from here. Gonna go straight through. Since this is a double multiplicity, it's gonna do something like that, and then it's going to go something like that. Okay. Now it's an overall shape. I'm sure the one we're going to get will look different, but similar. Okay, these might be bigger, the bumps and stuff, but we're going to get kind of a look like that. So let's see if that actually is in fact what we get. So I have to remember this: x minus 2, x plus 1, and x minus 4. Let's see. So let's go over Desmos. I'm getting a new Desmos anyway. So we'll just say y equals, and we'll graph that first one. It was x minus 2, right? And that was squared. Actually, there was a negative 2 on the front, so let's put that in there, negative 2. So we see that going on. Then there was x plus 1, right? So we kind of see that going on. And then finally, there was x minus 4. Sometimes it's by, and that was a cubic. So I'm going to go with that, and we'll make that a 3. And we see I was pretty close. Let's see if I come down. Again, the size of the, wow, that goes way up there. Yeah, it's hard to see. But yes, it's coming down from below, goes straight through at negative 1, does sort of kisses the x-axis, bounces, touches, and goes up. And then we see this little sort of a little bit of a S sort of thing as it goes through at 0 at 4. But we also see in behaviors, as x goes towards negative infinity, y is going towards negative infinity, right? Here's y is going down. And at the other end, y is also going down here towards negative infinity. Going this way, this is x going towards negative infinity, and this is x going towards positive infinity to the right. And we get the same general shape. Okay, back here, and we're back in shape. Okay, they're not all given to us in nicely factored form. So this one, we really have no, I mean, it's difficult to find out where the zeros are. We could try to factor it, but again, with this one, let's just go ahead and go to the Desmos. Those Desmos will do a good job with this. But let's do what we can do, which is maybe try to predict in behavior. We see that it's got a degree of 3, so that's an odd degree. We're going to get the saguaro cactus sort of look. And the leading coefficient, it's invisible, but it's a positive one. So we got a plus 1, we've got an odd, which is a 3. So overall, it's going to, negatives are going to be matching up, negatives and negatives. And then it might go something like that, and then positives and positives. So we get something like that. We'll see. Okay, I'll take care of that update later. So let's see, we got x cubed minus 5x minus 4 plus 20. I think it'll factor, but again, a lot of times just go ahead and use the Desmos because it's going to get you there faster. X cubed, right, to the third, and then it was I think minus 5x squared. I'll have to go back and check, and I can't remember if it was plus or minus. I think it was plus 4x, and I think it was plus 20. But let's go back and check. Negative, oh, negative 4x as well, and a plus 20. Which one am I working? Yeah. So change that positive to a negative. But we see overall, we have to we get the swirl cactus look of a one down and one up, just like we said. But this also helped us to find the zeros. And since we do have integer values, this tells us actually it will factor. And it shows us as they're going through each of these zeros as a multiplicity of 1, which would make sense. We can also find minimums and maximums. That's for sort of another lesson down the road, but we're not going to worry about those. What we're interested in is the zeros, each having a multiplicity of 1. And so from those zeros, what we can look at, see if I can keep those zeros in there. I guess as soon as I go there, I like to freeze it. So that's where you take a screenshot, -2, 2, and 5. What we could do is, what we should get is we get the opposite of those, right? So we're going to get x plus 2, x minus 2, and x minus 5. What would be kind of cool to do is to see if we get the same graph, which I think we should, because that should all factor out to that. So what I want you to see, though, is that once you do the graph, if you get integer values, it actually will help you with factoring. So that's why sometimes let's just go ahead and graph it, because we get more information when we do that. Okay, and then what, x minus 5. And it is, see, it's right on top. If I turn it off, we got the red, turn it on. So the factored form and the polynomial form. Well, they're both polynomials, but factored form and non-factored form, I guess is what I should say. Later. Let's go later. It's probably going to keep bugging me until I do that. So anyway, we could do that. Multiplicities, all of them had a multiplicity of 1. We can see that as it went straight through. We could kind of see in advance what the end behavior would be, but that's about it. And we'll just take a look at this last one, where we could actually probably do a little bit more, but again, in behavior, we see the degree is 3, so it's odd, it's negative, so we're going to get a swirl cactus, but this time it's going to start at positive infinity, maybe loop and come down to negative infinity, something like that. Now, this one is, I could see a little bit of easier way to factor, so I'm going to go ahead and do this. But again, if you would go ahead and use Desmos, you'll be able to find those zeros fairly quickly. What I'm going to do is I'm going to factor out a minus x. So here's minus x. So if I factor out a minus x, what's left in this first one will be x squared. The other one would be negative 2x, because I took an x out and a negative x, so then positive becomes negative. And this 48x, since I factored out the x, a negative x, it's going to be negative 48. Okay. This last part we'll factor. 48 is 6 times 8, and since we're subtracting, since it has this negative, 6 minus 8 gives us 2. So then I could say I've got a negative x, and then I'm going to get an x and a 6, an x and an 8, and I'm going to look at the middle term as negative, so the bigger value has to be negative, but we need one of them positive, one of them negative. That's how I get a negative 48. So this factors. Again, go ahead and FOIL this out to check. That will be it. So from this, I can see I'm going to get a 0 whenever x equals 0, right? That's from this first part. I'm going to get a 0 when x plus 6 equals 0, so that's going to be when x equals negative 6. And I'm going to get another 0 when x minus 8 equals 0. Add 8 to both sides, x equals positive 8. So we will get zeros there. Because of the degrees, right, these are all 1 degree, degree of 1, they will have all a multiplicity of 1. Okay, so this will happen at 8. This actually will happen at 0. I could probably draw this more accurately, and then there's going to be 1 here at negative 6. So actually what I'll do is, let's just move the y-axis. Yeah, there we go. That's gone. Now it's pretty accurate. And it should look a lot like this. A negative 6 passing through a 0 at the origin, passing through 8, and going down that way. And again, we can verify this with the Desmos calculator. If you want to keep moving ahead, do the Desmos calculator first. However, do come back and see why it looks the way it looks. Okay, so this was what? This was y equals, what was it? It was x cubed. And then it was, I forgot, x minus x cubed plus 2x plus 48. Okay, so it's minus x cubed plus 2x squared, right? And then plus 48x. And again, I see my zeros right where we had mentioned they would be. Now the graph itself is so big, it's really stretched out, isn't it? Not much I can do, but yeah, it comes from here. So this is y is going to positive infinity when x is going towards negative infinity. So again, you get the opposites. And this key part here is y going down to negative infinity as x goes towards positive infinity. Okay, so we can see the end behavior here. It's just very messed up. And again, you could graph the factored form, and you would see exactly the same thing. So either way, it will work for you. So that brings the end to our direct instruction for Module 8. Again, we're going to encourage you to complete those learning activities, follow through on them. We'll see, again, the thing to focus on is the degree and whether the leading coefficient is positive or negative. We do have the resources of online tutoring. We have our instructor office hours during the week. Check on those. And then also you can work with the peers and your instructor through the discussion forums by posting any questions you have. Now, you may not get an immediate answer, but you might get it sooner than you might think, because other people are popping on as well. So keep up the good pace, keep moving forward, and that will be the end for Module 8.